So picture a massive, sprawling data center, like aisles upon aisles of server racks blinking with thousands of tiny blue and green lights.
Right, the classic beating heart of a global business, just incredibly loud with all those cooling fans.
Exactly. It's processing millions of transactions, storing terabytes of customer data. But now I want you to imagine a catastrophic power grid failure or, a systemic network
The
collapse.
total blackout.
Yeah, in a fraction of a second, all those blinking lights just go dark, the fans spin down, the room goes completely dead silent. What happens next?
Well, the sheer silence of a dead region is it's pretty deafening for a business. I mean, it
Mhm.
triggers an immediate cascade of operational nightmares.
Oh, for sure.
And in that exact moment, an organization finds out whether they actually have a resilient architecture or if they just bought a really expensive collection of servers.
And that harsh reality is exactly the focus of our deep dive today. We are synthesizing a stack of cloud architecture documentation covering disaster recovery or DR frameworks.
Essential reading, really.
Definitely. We're looking specifically at AWS methodologies, the underlying mechanics of how data physically moves, and those brutal cost-benefit trade-offs involved in keeping a system alive. The mission today is, well, to build a survival guide for when everything burns.
I like that. Because frankly, hope is not an architecture strategy.
No, it is not.
When we strip away all the marketing jargon, disaster recovery is entirely about buying a business insurance policy.
An insurance policy. Okay, I like that metaphor.
Yeah, and just like real insurance, you've got different tiers of coverage. The cheaper policies, they require a massive amount of manual paperwork and they take a really long time to pay out.
Right.
But the premium policies, those get you back on your feet instantly. The catch is you are paying that exorbitant premium every single month, regardless of whether a disaster ever even strikes.
So before you can even shop for an insurance policy, you have to know exactly what you are insuring, right? You have to quantify what a loss actually looks like to your specific business model.
Exactly. You need boundaries.
So I want you, listening right now, to think about your own infrastructure. If your primary database melted down right this very second, do you actually know your tolerance for loss?
Most people don't, honestly.
In cloud architecture, that tolerance is defined by two fundamental metrics, RPO and RTO.
And literally everything we discuss regarding architecture rests on these two numbers. So RPO stands for Recovery Point Objective, and RTO stands for Recovery Time Objective.
Okay, let's break those down.
Before a single line of infrastructure as code is even written, the business stakeholders, not just the engineers, have to define these limits.
I always visualize RPO, the recovery point objective, like playing a massively long, incredibly difficult video game. Your RPO is essentially asking, well, how far back was your last save point before the game crashed?
That is a perfect way to look at it. It is the exact measure of acceptable data loss quantified in time.
So time is the metric here.
Right. If your primary database only backs up to another region, say, every 4 hours, and your production environment goes up in smoke right before the next scheduled backup, you have permanently lost 4 hours of data.
Ouch.
Yeah. Your RPO in that architecture is 4 hours. Now, for an internal corporate wiki, losing 4 hours of edits might just be a minor annoyance.
Sure, somebody has to retype a memo.
Exactly. But for a global financial trading platform, losing 4 hours of transactional data is an extinction-level event.
Wow. Yeah, in that gaming scenario, if my last save was 4 hours ago, I'm throwing the controller across the room. Like I've lost all that progress.
And in a business context, that lost progress translates directly to lost revenue, shattered customer trust, and, potentially massive legal liabilities.
Which brings us to RTO, the recovery time objective. So, extending your gaming analogy, if the console crashes, RTO is the measure of how long it takes to reboot the system.
Right. Load the operating system.
Launch the game, pull the save file, and actually get back to a playable state.
Loading screen of doom, basically.
Exactly. It's the sheer physics of booting things back up.
In the engineering world, RTO is the maximum allowable downtime. It's the clock ticking from the exact millisecond the outage occurs to the moment the system is fully functional and serving customer traffic again.
So it's about availability.
Right. If an e-commerce platform goes down during, say, a peak holiday sale, an RTO of 6 hours means a massive hit to the quarterly earnings.
Okay, so we establish our maximum acceptable data loss, which is our RPO, and our maximum allowable downtime, our RTO.
Yep.
Armed with those two constraints, we go to the cloud market to buy our insurance policy. The documentation outlines 4 distinct disaster recovery strategies.
The 4 tiers.
Let's break down these tiers, starting with the baseline. I'm going to act as the CTO of a rapidly growing software as a service company, okay?
Okay, lay it on me.
My primary AWS region has completely failed. Gone. Walk me through my options. What's the cheapest way out of this?
Well, the first tier of insurance is backup and restore. This is the absolute cheapest policy on the market. It is exactly what it sounds like.
Just saving files somewhere else.
Pretty much. You are periodically backing up your data and your machine images to a highly durable storage service like Amazon S3 in a secondary region. When your primary region fails, you have the data safely stored elsewhere.
But, the friction here is the RTO, isn't it? Restoring a multi-terabyte database from S3 isn't just clicking a button and waiting a few seconds.
Not at all.
I mean, I have to provision new virtual machines, hydrate new storage volumes with that backup data, configure the networking, route the traffic. Even with heavy automation using something like Terraform, pulling that much data out of cold storage takes time.
It does.
My RTO is going to be measured in hours.
Often many hours, yeah. You are essentially rebuilding your production environment from scratch in a new geographic location. It is incredibly cost-effective because you aren't paying for idle compute resources, but the trade-off is a grueling recovery time.
Yeah, hours of downtime won't work for my SaaS platform. Customers will just flood the support lines. I need something faster. What is the next step up?
So tier 2 is the pilot light strategy. The metaphor here is think of the gas heater in a house.
Okay.
The main heating elements are completely off, which saves you energy and money, but there is a tiny, continuously burning flame, the pilot light.
Right, so it's ready to go.
Exactly. When the house gets cold, that tiny flame instantly ignites the main system. Architecturally, you keep your absolute core, stateful services like your database running continuously in a secondary region.
Okay, I follow.
The database is actively receiving data replication from your primary region. However, your stateless infrastructure, like your fleet of web servers and application servers, they are completely shut off.
Got it. So I'm paying a higher premium because I'm keeping that database instance alive and paying for cross-region data transfer.
Right.
But when my primary region fails, I don't have to wait hours to restore data from cold storage in S3. The data is already sitting there, warm, in the secondary region.
Yep, it's ready.
I just run my automation scripts to spin up the application servers around that existing database.
And that shrinks your RTO from hours down to tens of minutes. You just have to wait for the compute instances to provision and pass their health checks.
The hidden danger I see with Pilot Light, though, isn't the AWS bill. It's configuration drift.
Yeah.
If I leave my secondary region shut off for 6 months, my primary region is constantly evolving. Engineers are updating machine images, patching operating systems, modifying security groups.
It changes daily.
Right, so if the secondary region's automation scripts aren't rigorously tested and updated alongside the primary, I'm going to hit an outage, try to ignite my Pilot Light, and the system will just fail to boot because the configurations are completely out of sync.
That is a highly critical operational insight. I mean, a disaster recovery plan that isn't tested is really just a highly structured wish.
A structured wish?
Yeah.
Yeah.
Configuration drift is the silent killer of the pilot light strategy. And this is exactly why many organizations move to Tier 3, which is warm standby.
Warm standby feels like keeping a backup engine idling in the driveway at all times.
That's a good way to put it. It is a fully functional, live copy of your entire production environment running continuously in a secondary region. But, and this is key, scale down to the absolute minimum footprint.
So it's not a full replica of capacity?
Right. You might have just 1 or 2 small web servers running alongside your replicated database. It is actively processing a tiny fraction of user traffic just to ensure everything is working perfectly.
Oh, I see. So configuration drift is eliminated because the environment is continually active and receiving the exact same deployment pipelines as production?
Precisely.
When the primary region goes dark, the secondary system is already fully booted. I just have to tell my auto-scaling groups to immediately ramp up capacity to handle the sudden influx of all global traffic.
And your RTO is now down to just minutes. Literally just the time it takes for those auto-scaling groups to add new compute nodes. But, the premium is substantial. You are permanently paying for idle scaled-down infrastructure in a second region.
Let's push this to the absolute limit, though. Say my platform handles financial trading. Even a 5-minute auto-scaling delay could cost millions in missed trades. I need an RTO of essentially 0.
Well, Then you purchase the ultimate, most expensive policy on the market, multi-site active-active.
Active.
Yes, you run your entire infrastructure at full production capacity in two completely separate geographical regions simultaneously. They're both taking live customer traffic, splitting the global load.
Okay.
If one region suffers a catastrophic failure, your users are instantly automatically routed to the surviving region. You experience practically zero downtime.
The financial cost is staggering, obviously. I mean, you are literally doubling your infrastructure footprint. But the engineering complexity is what really stands out to me. Keeping two separate global regions perfectly synchronized in real time is, well, it's a massive physics problem.
It requires an entirely different class of architecture,
Oh.
which frankly forces us to look under the hood of the actual mechanics. I mean, an insurance policy is useless if the bank can't process the payout.
Right.
A disaster recovery strategy is useless unless you have the underlying mechanics to physically move the data across the globe and redirect your users.
Let's talk about that physics problem then. Moving data from a data center in Virginia to a data center in, say, Ireland sounds exhausting. Why can't I just achieve my RPO by renting two data centers in the same city, putting a massive fiber optic cable between them, and replicating my database locally?
Well, that design exposes you to a shared blast radius.
Blast radius.
Yeah, two data centers in the same city are highly likely connected to the same regional power grid. They sit on the same tectonic plate. They rely on the same regional internet service providers.
Oh, I see.
A localized natural disaster or a massive utility failure wipes out both buildings simultaneously. True disaster recovery requires geographic isolation.
Got it. So I have to separate my primary and secondary environments by hundreds or thousands of miles to escape that blast radius. But that distance introduces latency.
The speed of light is undefeated.
Right. So how do we actually move the data fast enough to meet a low RPO without destroying the performance of the application?
Okay, so if we are dealing with a standard relational database, like Amazon RDS, and we are utilizing a warm standby strategy, the mechanic we rely on is the read replica. You provision a secondary database in your backup region.
Oh.
The primary database streams every single transaction log to that replica.
But the key here is that the replication is asynchronous, right? And it has to be asynchronous because of the speed of light.
Exactly.
If I use synchronous replication, the primary database in Virginia has to wait for an acknowledgement from the replica in Ireland before it can commit the transaction and tell the user it was successful.
Which takes forever in compute time.
Right. That round trip across the Atlantic Ocean takes roughly 80 milliseconds. Adding 80 milliseconds of latency to every single database, right, would completely cripple a high-performance application.
Which is exactly the reason synchronous replication is largely restricted to local, close proximity setups. With cross-region asynchronous replication, the primary database commits the write instantly and then just fires the transaction log across the ocean in the background.
So the gap between the primary commit and the replica receiving the data is my replication lag.
Yes.
And that replication lag literally dictates my RPO. If the primary region explodes and the replica was 2 seconds behind, I have permanently lost 2 seconds of data.
And we also have to factor in the mechanics of the failover itself. When the primary region goes down, the read replica doesn't just instantly become the primary.
There's a process.
Right. You trigger a promotion process. The replica has to sever the replication link, apply any remaining transaction logs it has buffered, reboot, and then reconfigure itself to accept write operations.
How long does that take?
That process takes a few minutes. That database promotion time is actually your primary RTO bottleneck in a warm standby setup.
But what if I am paying for the multi-site active tier? I can't have a primary and a read replica because both regions need to accept write operations simultaneously. Users in Europe are writing to the European region, and users in America are writing to the American region.
And this is where standard relational databases just break down. You run into massive conflict resolution issues.
Because of collisions.
Right. What happens when two users on opposite sides of the planet try to update the exact same inventory record at the exact same millisecond?
A traditional database would try to lock the row, which would require cross-continent communication, reintroducing that horrible 80 millisecond latency we just tried to avoid.
Exactly. This is where managed services like DynamoDB Global Tables become essential for active architectures. DynamoDB is a multi-master, fully managed NoSQL database.
Okay.
It accepts writes locally in both regions simultaneously, keeping latency at single-digit milliseconds.
But how does it resolve the conflict if two writes actually collide?
It relies on a last writer wins reconciliation mechanism based on precise timestamps. It doesn't lock the database across the globe. It accepts the writes locally, maintaining that speed, and then reconciles the collision at the storage layer entirely behind the scenes.
Wow.
It is the engine that makes a globally distributed active architecture feasible.
So we have the data layer solved. The data is replicating asynchronously, or we are using global tables for active. But there's a glaring missing piece here.
What's that?
The primary region in Virginia goes completely dark. The servers in Ireland are fully primed and ready. How do the users actually know to go to Ireland? Their browsers are still trying to connect to the dead IP addresses in Virginia.
Good catch. This brings us to the traffic cop of the Internet DNS, specifically a service like Amazon Route 53. To route traffic dynamically during a disaster, you configure Route 53 with failover routing and tie it to automated health checks.
Oh, so Route 53 is constantly pinging the load balancers in Virginia, asking, are you healthy? Are you accepting traffic?
Exactly. The moment the Virginia region fails to respond, the health check fails. Route 53 instantly stops returning the IP addresses for Virginia and starts resolving user queries to the IP addresses of the standby environment in Ireland. The user types the URL into their browser, and the DNS dynamically reroutes them away from the fire.
But there is a massive trap here regarding DNS that catches so many engineering teams, TTL, or time to live.
Oh, absolutely, the caching problem.
Every DNS record has a TTL, which tells user browsers and global internet service providers how long they should cache the IP address before asking Route 53 for an update.
Right. And if your TTL is set to, say, 24 hours, Route 53 can update its records instantly upon a failure, but millions of users' browsers will just continue trying to reach the dead Virginia data center for another day.
Because they cached the old IP address.
Because they cached it.
That entirely destroys your RTO.
It completely nullifies the entire disaster recovery plan. For your DR routing records, the TTL must be extremely low, typically 60 seconds.
The trade-off being that a 60-second TTL forces client browsers to constantly query Route 53 for the address, which massively increases your AWS bill for DNS queries.
Which is just another part of the premium you pay for a resilient insurance policy. Every single mechanism in disaster recovery requires a trade-off between cost, complexity, and recovery speed.
Speaking of traps, there is one specific architectural misconception that the documentation warns about consistently. It's this psychological trap that provides a false sense of security.
I know where you're going with this.
I'm talking about confusing local high availability with global disaster recovery.
The multi-AZ trap.
Yes.
So in AWS, regions are broken down into availability zones, or AZs. An availability zone is essentially a distinct, physically isolated data center, or cluster of data centers, within that overarching geographic region.
Right. And the UI in the Cloud Console makes it incredibly easy to just check a box that says deploy multi-AZ. An engineering team checks that box, deploys their database across 2 or 3 availability zones within the Virginia region, and tells their stakeholders, we are highly available, we have backup servers, our disaster recovery plan is complete.
And they were dead wrong. I mean, they have built local resilience, which is critical, but they do not have a disaster recovery plan.
It's not the same thing.
Not at all. Multi-AZ protects an architecture against a localized hardware failure. If a server rack catches fire, or a backhoe cuts a fiber line to a single data center, the load balancer shifts traffic to the other availability zones seamlessly. It provides high availability.
But the blast radius constraint still applies. Availability zones are typically separated by tens of miles, not thousands.
Right.
If a massive regional event occurs, a severe hurricane, a wide-scale power grid collapse, or a systemic software bug that corrupts the entire region's control plane, all of those availability zones go down simultaneously.
Think of it like this. Multi-AZ is the spare tire in the trunk of your car. It helps you survive a localized puncture.
Okay.
Disaster recovery is having an entirely separate, fueled-up vehicle parked in a different city for when your primary car gets crushed by a falling tree.
That's a great visual.
You need high availability to handle routine hardware failures without waking up the engineering team at 3 a.m. But you need cross-region disaster recovery to ensure the business survives a catastrophic region-wide failure. They solve entirely different failure modes.
Let's synthesize everything we've covered by looking at a few distinct architectural scenarios.
Let's do it.
We have the business requirements, the RPO and RTO metrics, the 4 tiers of insurance, and the mechanical realities of data replication in DNS. Let's see how this dictates system design in practice.
Ready when you are.
First scenario. We are architecting an internal corporate intelligence tool. It processes massive batches of historical data to generate monthly forecasting reports. The business stakeholders state they have a high RTO tolerance. They can afford the system to be down for up to 24 hours in the event of a regional failure.
Okay, well, with a 24-hour RTO, spending significant capital on idle compute resources is basically architectural malpractice.
I completely agree. So the correct mapping here is the Tier 1 strategy backup and restore. The architecture would utilize continuous data snapshots stored in cross-region S3 buckets. We leverage infrastructure as code templates.
Right.
If the primary region fails, the engineering team has a full 24 hours to calmly deploy the templates in the secondary region, provision new analytical clusters, pull the data from cold storage, and resume processing. We meet the business requirement while keeping the operational cost incredibly low.
That is highly efficient engineering. Simple and cheap. Okay, second scenario. You're managing a regional ticketing backend for live entertainment. A 24-hour outage is completely unacceptable, as it would block ticket sales across multiple time zones.
Okay.
The business requires a moderate RTO. If a region fails, the system must be fully operational within 15 to 30 minutes.
All right, that 15 to 30-minute window places us squarely in the pilot light or warm standby territory. The decision really hinges on the complexity of the application stack. I would lean toward warm standby. We provision a cross-region RDS read replica to handle the asynchronous data replication.
Good call.
And we deploy a minimal, scaled-down footprint of our application servers in the secondary region to avoid that configuration drift we talked about.
But remember, the operational overhead here isn't just the AWS bill. It's the actual orchestration of the failover.
Exactly. When the disaster strikes, the recovery isn't magic. Route 53 health checks trigger the DNS failover, but we still have to execute a runbook to promote that read replica to a primary database, which takes a few minutes, and trigger our auto-scaling groups to ramp up the application servers from a minimal state to full capacity. That sequence of events easily fits within the 30-minute RTO, provided the runbook is automated and heavily tested.
Spot on. Okay, final scenario. You are architecting the transaction processing engine for a global ride-sharing application. Millions of concurrent drivers and riders rely on the platform.
High stakes.
Very. The business demands near-zero downtime and near-zero data loss. An outage of even 2 minutes results in massive revenue loss and critical safety concerns for stranded users.
Then we have to deploy the multi-site active architecture. The traditional relational database is out. We transition the data layer to DynamoDB Global Tables to enable simultaneous multi-region writes with millisecond latency and automatic conflict resolution.
Yeah.
We deploy full-scale stateless application clusters in both North America and Europe. We utilize Route 53 latency-based routing to direct users to their geographically closest region for speed.
And the failover.
We combine that with failover routing to immediately swing the global traffic to the surviving region if a health check ever fails.
The architecture is fully symmetrical. Both regions are processing traffic, both regions are writing data, and the state is globally synchronized. It really is the pinnacle of resilient design.
It requires immense engineering discipline to deploy application updates to an active environment without breaking the global state. But, it mathematically guarantees the survival of the platform.
It does.
We establish our data loss limits, our downtime limits, select the corresponding tier of insurance, implement the physical mechanics of replication and DNS, and ensure our design isolates us from regional blast radiuses.
That framework provides a highly structured analytical approach to surviving a catastrophic failure.
So, to you, listening right now, take a hard, honest look at the infrastructure powering your own projects. Have the uncomfortable conversations with your stakeholders. Do you actually know your RPO and RTO?
Probably not.
Have you tested your failover runbooks? Or are you operating under the psychological trap of multi-AZ? Just crossing your fingers and hoping the region never goes dark?
Determining your true resilience is a vital exercise. But I do then leave you with a final, slightly provocative paradox to ponder as you review your architecture.
Oh, I'm intrigued. What is it?
Well, we established that multi-site active-active is the ultimate, most resilient insurance policy for near-zero downtime because it seamlessly replicates data globally in milliseconds.
Right, it's the gold standard of cloud architecture.
But consider the failure modes. We have insulated the system against hardware failure, power loss, and natural disasters.
Yeah.
What happens when the disaster isn't physical but logical? What happens when a catastrophic human error or a corrupted software patch enters the system? If a senior engineer accidentally runs a script that drops your entire global customer database, Does that ultimate active architecture simply guarantee that the catastrophic deletion replicates itself globally to every single data center in milliseconds before anyone can even hit the stop button?
Oh, wow. A perfectly engineered system instantly and flawlessly destroying itself on a global scale.
Something to think about.